Hey everybody, and welcome back to Linear Algebra Online. So this is one of these videos that I really enjoy doing because it's one of these kind of places where you can really see some really beautiful connections between what we're doing with orthogonality right now and what we've talked about with subspaces. So there's this really cool natural connection between subspaces like that you know of well, the null space, the column space, the row space. You don't know this one yet, but I'll talk about that. And it turns out that there's a very nice natural connection with those and orthogonal complements, basically. So this picture kind of sums it up right here, but it's also written down right here. So if you have an m by n matrix, okay, the orthogonal complement of the row space of A, all right, so row space of A over here, is the null space of A, right? And the orthogonal complement of the column space of A, all right, is the null space of the transpose of A, okay? So in symbolic form, this is the symbol for orthogonal complement. The orthogonal complement of the row space of A is null space of A, and the orthogonal complement of the column space of A is the null space of the transpose of A. And this picture is a little deceiving because it doesn't have to be a linear, null space or something like that. You could absolutely have some sort of 3 by 3 matrix, and we've seen examples like this. You could have 2 dimensions basically go to 0, right, and 1 dimension transfer. And in terms of this, then, that would mean that the null space is 2-dimensional, right? It's actually more like the plane. And then the column space, which is the space that we basically conceptually think of as the stuff that has transferred after the transformation, that would be a line, right? So another thing I'm going to show you is there's a connection between this subspace and the column space, and then there's a connection between this subspace and this thing, the row space. So a lot of stuff to unpack here and a lot of really important things, but I wanted to start with just kind of doing a quick refresher on the 3 you know and talk a little bit about this thing you don't know. Not too much to say about the null space, right? I mean, it's just the if you have an m by n matrix, null space is the set of solutions of the homogeneous system AX equals 0, basically just the vectors that get sent to 0 right after the transformation. So A is applied and some stuff goes to 0. The column space is just the span of the columns of the column vectors, right? So this is conceptually what gets transferred what doesn't go to 0, basically. This is the stuff that is non-trivially sent through A, we'll say. The row space is the span of the row vectors of the matrix, okay? And it's really like the space that you start with. So it's just like if you had a matrix, let's do something like this kind of thing. Let's just say you have a matrix 1, 2, 3, -1, 7, and pi, because that's a good number. This being a 3 by 2 matrix means that we're basically starting in R2, right? And we're getting sent to R3. So the column space is going to live in R3, right? And the row space is going to live in R2. The reason you can see that, you can just think of it in terms of how you multiply a matrix and a vector. This being a 3 by 2 would mean that this vector here needs to be a 2 by something, right? It could be just a 2 by 1. It could be 1, 1 or something. But the space that you start in, which is, just the row space again, the span of the rows, would be like two-dimensional here. And then this matrix would map a vector like that to R3, or at least a subspace in R3. It does not have to map to all of R3, definitely, because some stuff could go to 0, right? And I'm going to talk about this one in a second here. So what I want to do here is just, symbolically, like we know this pretty well, right? That's the null space of A, just any vector x that A operates on and goes to 0. You can do that for these two as well. So I want to kind of write that down. So, basically we could say that B is in the column space of A if and only if, A, let's just call it X again. It's fine. It's like a different thing. It doesn't have to be this X, right? Equals B or something, right? So, symbolically, this is kind of how we write things in the column space. We just say A operates on some vector, and it ends up B, and B is the thing that's in the column space, right? We could do a similar thing for the row space, right? But if we wanted to really be analogous here, we would, if the matrix was like a, if we have some 3 by 2 again, like what was the 3 by 2 I had over here? 1, 2, 3. And then -1, 7 pi. So if we had this matrix, right, and we multiply by x, right, and we get some vector b, that is really the columns here operating on this thing, and you're getting this other thing in the column space, right? If we wanted this like symbolic thing that I have written down here to apply the row space, you're going to have to transpose this, right? You're going to have to transpose it, and so, you could kind of say something like A is in the row space of A if and only if A transpose times X is equal to A, right? So now, if you just take this thing and you flip it around, I'm just going to, here, we'll do it this way. This is the easy way. So if I just take the transpose of that, right, multiply by this vector and get, now it's something else. It's A, I'm saying. But that is symbolically like how we describe the things in the row space of A, okay? And that kind of leads us to this thing that we don't really know about yet. So the left null space is actually just, there's a reason it's called left null space, and I'm going to actually show that here in a second, but the left null space is really just the null space of the transpose of A, okay? So, literally it looks like this. It's like if you took, there's kind of a connection here and here. Well, imagine now take this and just, instead of A being just some arbitrary vector, if we thought of it as AT x equals 0, that is all this thing is. That's all the left null space of A is, okay? And you kind of see it right there, but I'm actually going to explain this a little bit more detail in a second right now. But the left null space part is basically tied to this notation right here, which I'm going to show in a second. But it is good that you can kind of see these symbolic forms of these subspaces. So null space, right, pretty intuitive. Column space, something's in there in the column space of A if A just operates on a vector X and you get to that thing B. And then the row space, because if you do that idea, but that wouldn't really be the row space if you just, literally copied this down or something. You need to switch rows and columns in order to have this trick work down here. So we're switching rows and columns, and then this will all work out nice. And then you can describe this thing called a left null space, which is just this idea for A transpose. That's all it is, okay? All right, so this is just another picture, and it looks kind of scary when you first see it, but it's another picture of this, and I kind of like it a little bit more for a few reasons. So they're showing here that like the null space of this like can be thought of as A, right? Null space of A, that they're still perpendicular. That's what this little notation is. But it's not saying that it has to be linear or something like that. You know, not that this really says that. It's just symbolically trying to show that they need to be perpendicular. But that's what they're trying to convey here. And likewise, the column space of A is perpendicular to the left null space, or just the null space of the transpose of A. And, you know, a lot of this other stuff is actually, I'm going to bring it up kind of later on, but this is just showing some of the mapping, right? So if you have some x sub r in here, some vector, A operates on it, and you get B. B, like I said, is in the column space over here, right? You know, things like it's showing that the zero element will go to the zero element, which is shared by both. That's really what that's trying to show right there. And the dimensions, there's an important kind of diagonal feature to the dimensions, okay? The dimension of this, if it's R, then the dimension of this will be m minus r. And the dimension of this, being n minus r, is linked to this, which is equal to the dimension of it being r. And that stuff I'll kind of get into in a second when we do an example. But for right now, I want to do two things. I want to show why these spaces are perpendicular, and I want to show why this one is called a left null space. So let's just do the left null space first, because it's kind of quick and easy. So the left null space was just defined as the vectors, right, that the transpose sends to zero. So what we're just going to do is just take the transpose of both sides, right? And then we would have to use like the whole socks and shoes thing. So we get x transpose A transpose transpose, which is just A, and then the zero vector there transposed, right? And I mean, this is basically it. It has the kind of null space. So this thing is just like it has the structure of a null space, right? Of A, but it's on the left. It's like the null space of A on the left, and so it gets the brilliant name of left null space. This is if you think about it, it actually does need to be written this way, so I might erase this just for the sake of space, but if A is m by n, right, then A transpose is n by m, right? N by m, sorry. And then x is like a vector that's like has to be m by 1. And so then the zero vector there is like n by 1, right? And so if you transpose both sides, right, so on this line, then x should now be a 1 by m, and A is m by n, which it was, right, to start off with, sorry. And then you would get a 1 by n zero vector, basically. So, like, computationally speaking, this looks kind of funny, I think, but it actually does need to be written specifically that way. It's kind of important. All right, so the next thing I want to do here is just show a little bit about this piece in here, okay? So if we start with the null space of A, okay, notice that you're basically, you want to think of this as a column vector, right? And so it's some like, well, me make some more room here. So we know A is some, what was it, m by n matrix. And then X you want to think of as like an n by 1, which is zeros here. The m by 1 0 vector, right? And so the way you would do this, right, if you have a column here, you're just doing rows times the columns, right? So you've got all these like rows in here. I mean, specifically, you've got m of them, right? And the way you just do matrix multiplication is a dot product, right? This is really just a dot product. And what it's doing is it's dot producting specifically rows dotted with a column vector, right? And you're getting 0, like every single time, right? You're getting 0. And so that is what it specifically means, right, to be perpendicular. And so that is why these two things, the row space and the null space of the matrix are perpendicular. The orthogonal complements, if you want to be like fancy with it. For the other side here, we can sort of just do the exact same thing, but do it with a transpose. Like we're just going to start with the left null space, right? So here, the way I could kind of think of this is I have a matrix, but now it's an n by m matrix, right? And it's dotted with an m by 1 column vector, and it's equaling 0, just all the way down, and that's n by 1. And so now, it's still rows here, but the important part to kind of notice is that the rows here, these rows of a transpose are the columns of A, right? And so that's not really good notation, but because that is what the column space is. But the span of those columns, these red rows, which become columns in A, is the column space, right? And so the same way that there's this dot product, there's this dot product here, but you're dot producting really columns of A with this vector and getting 0. And so the things in the left null space are perpendicular to the column space of the matrix. So that hopefully paints some kind of understanding of what these things are. And then I want to just sort of show a few examples with them now. So this is really kind of a classic linear algebra problem. Just find the bases for the 4 fundamental subspaces of a matrix, okay? And so just a few things to kind of keep in mind. So I'm going to kind of draw a rough sketch of that last slide. So I'm trying to draw like this thing, right? And we know because this is what is it actually? It's a 4 by 5 matrix, that we are going to be going from R5 to R4 in this transformation, right? And like this is the null space of A, and this is what gets transferred in A. And so these two things should add up together. It's just like the rank theorem, right? And then these two things should add up together. But also, these two things should add up to what you start with, R5. And these two things is what should add up to R4. So this is going to be something that we can kind of fill in as we go and check that everything's basically adding up together. So some of this is kind of review because we did this back in like Unit 3. But to find a basis for the column space of A, the way that we just did this before is we can just RREF A, and we would get this. And what we did is we basically took a look at the columns where there's like a leading 1, right? And where those kind of backtrack to in the original matrix, you can just take those columns as basis vectors, right? So if I call this column like U1, this one U2 or something, and this U3, then the column space of A can just be described as the span of U1, U2, and U3, okay? So what we just figured out so far is that we should put a 3 right in here, right? So the column space of A is dimension 3. And so we should hope that this should be a 2, right? When we get to the null space of A, because we know 5 dimensions need to be transferred, and we just saw 3 transfer. For the row space of A, right, that is equal to the column space of A transpose, right? That's kind of how we did this before. And so to find a basis for the row space of A, the easiest way here is to just do RREF of AT and analyze that thing. So this is what we get from that. All right, and same kind of thing here. So I'm going to, just sort of pull out this, and this, right? And so those 3 rows in the transpose, right, is what we can use as the first 3 rows in the transpose is what we can use, or first 3 columns in the transpose is what we can use as a basis for the row space, right, of A. And the first 3 columns of the transpose would relate to the first 3 rows of A. And so if I call this row alpha 1, alpha 2, alpha 3, then the row space of A could be just defined by the span of alpha 1, alpha 2, and alpha 3. And so now we found this was a 3, right? We also know that this and this should add up to 4, because that's the dimension that we end in, right? So I think I'm going to move over to a new slide for the null spaces. So for the null space, right, that one is pretty straightforward. Basis for the null space of A, we just do the computation like A, well, here, I'll do it this way. So we just RREF A augmented with the 0 vector, right? Which is basically saying, like, what does X have to look like to get you the 0 vector? And we can sort of steal, this, because A augmented with the 0 vector would literally just be this matrix with a row of zeros over here. And so you can just do the kind of trick. Here, let me copy that over here. So, it would just look like RREF of A with a 0 there. But this is the kind of thing where we're just like, okay, x1 can equal minus x3 plus x5. x2 can be described as minus 2x3 minus 3x5. Well, x3 is just x3. And x4 is equal to minus 4x5. And x5 is, of course, just x5. And then you can do the thing like let s equal x3, t equal x5, right? And so our basis can just become so it's, here we'll start it this way. So x1 is minus x3, so we have minus s plus t, and then x2 is minus 2s minus 3t. X3 is just my s. X4 is minus 4t, and x5 is just my t. But then that splits naturally into -1, -2, 1, 0, 0. and then plus t times 1 minus 3, 0, minus 4, 1. So if I call this, I don't know, beta 1 and this beta 2, then the null space of A is equal to the span of those two basis vectors, okay? And so the null space of A, we just found was 2, and dimension 2. And so notice 2 plus 3 is 5, which is good. So now you've got to go do the exact same thing, but for the null space of AT, okay? And I don't have a lot of room here, but the computation is literally the same. You will get, if you do it, x1 is minus x4, x2 is minus 6x4, x3 is minus 3x4. And from that, if you parameterize that thing, you see that it's the a basis could just be the span of -1, minus 6, 3, minus 3, and 1. But nicely enough, the null space of AT is 1. And so if you look at all this, it all adds up really beautifully and really nice. It's like a Sudoku. That's how I think of this stuff. 2 plus 3 is 5, right? 1 plus 3 is 4. 2 and 3 over here is 5, which is the kind of transferred stuff, right? So 2 of the dimensions disappear, 3 get transferred. And then 3 and plus 1 is 4, which fits like perfectly with the picture here with all this stuff going on. So they're kind of a very beautiful, very nice chunk of subspaces. And anytime in math you see this word, you should take extra caution because it's something super, super important. It also lets us do some things just like, I'm not going to go through this whole problem, but I just kind of want to talk through what's going on, I guess, here. If you were asked to, so if you were given like a subspace, you were said that W is a subspace of R5, which is spanned by these 3 vectors, okay? Then you're asked to find a basis for the W perp, okay? What you can actually do is you can basically make like a matrix A, which is just built out of like W1 as a column vector, W2, and W3. And then what you can do is the column space of A, right, is just the column space of, so this matrix A is going to be perpendicular to the left null space, right? And so basically it's like, you know, I'm thinking of this picture that we had last time where we have some vector over here or whatever, but we wanted things like that's perpendicular to my plane, right? My plane is like my column space, and if I want a basis for the things like this that are perpendicular to that plane, I can just utilize the fact that I know the left null space is perpendicular to this matrix that's formed by sticking these 3 vectors in as columns. So I'm not going to go through it all because it's fairly straightforward, but you could basically just find a basis for the left null space, which is the same thing as just doing like RREF of T augmented with 0. And then just like over here, you know, you would do the same kind of thing where you would get this REF and you could describe x1, 2, 3, or whatever in terms of other things. You could parameterize it, and then you'd get some vectors, and those could be your basically basis vectors for the perpendicular subspace to W here. This kind of stuff just plays a role in so many areas in mathematics. I felt like I used it in a ton of different things all over in grad school and whatnot. So very good to understand these 4 fundamental subspaces. They're really, really big in math.